All right, good afternoon, everyone. My name is Austin Hickman. I'm a co-founder of Soctera and also a fifth-year PhD student in electrical and computer engineering at Cornell. And Soctera is developing power amplifiers based on aluminum nitride, and this aluminum nitride will enable next-generation wireless communication systems. So to begin, I'd like to show you this familiar image. You may have seen it in a TV show or a movie. There's a blip on the radar. Something's out there. But what's out there? Is it a car or a plane? Is it friend or foe? This one dot cannot supply that type of information. To get that type of information, you need to move to a radar system capable of much higher resolution. And to improve resolution, it is accomplished by increasing the frequency, in this case shown here with millimeter wave radar. This increase in frequency is defined as the frequency at which the radar operates. And it provides much more information about the object we're detecting. We can see what it is, we can see its orientation, and you could even tell the make and model of the vehicle. But there's a drawback to increasing the frequency of your radar system, and that's range. So these higher frequency signals interact much more heavily with the atmosphere. And as a result, they lose power as they travel through the air much more rapidly and soon dissipate beyond detection. And this pain point is felt, of course, in defense radar systems, but it's also felt in telecommunications. So in telecommunications, as many of you may know, there's been delays in the rollout of 5G. And one of the most significant issues that caused this delay in the rollout is the lack of range. So when you lack range, you need more towers to provide proper coverage. And more towers mean more maintenance and more complexity of your system. And for these reasons, in both defense and telecommunications, the millimeter wave revolution is shackled by limited range. So if our goal is to get more range, how do we do that? And the answer is quite simple. You supply your signal with higher power. And this task of higher power falls on the power amplifier, which can take a high frequency signal and takes a high frequency signal and gives it more power or juice right before it's broadcast. So if our goal is range and we get more range with higher power, what is limiting how much power the power amplifier can provide? And the answer to that is entirely the materials. So let's take a look and compare today's power amplifier materials with the relevant material metrics. One of the metrics here is for maximum power capabilities, one for thermal performance, which prevents overheating, and another for the maximum speed or frequency at which these materials can effectively operate. So first up is silicon. And silicon is attractive, of course, due to its maturity and massive economies of scale. But when you look at this graph, it's pretty clear that silicon falls short in all three phases. And as a result, when you take a look at this power and frequency chart here, you can see that the power provided by silicon rapidly falls off as well before we reach the millimeter wave frequency band. So let's introduce a new material, gallium nitride, or GaN. So GaN surpasses silicon in all three phases, and GaN is a new material that's just been really developed within the past 20 years. And as a result of this improved material performance, you can see that it is able to maintain high power up to much higher frequencies, just into the millimeter wave frequency bands before the power starts to, again, rapidly fall off. And to just give you an idea of the available market that is between the end of silicon and through GaN in this power frequency range, the GaN industry or GaN power amplifier market, which really just came from nothing to what it is today within the past 10 years, is today worth $750 million. And by 2025, so less than 5 years from today, is projected to be worth over $2 billion. So is there a material that can provide true high power performance across the millimeter wave frequency band for defense radar and telecommunications applications? And at Soctera, we believe that material is aluminum nitride. And then when we look at aluminum nitride's material properties, it's easy to see why. It outperforms GaN significantly in terms of the maximum power and in terms of the available thermal conductivity, which improves your device's ability to pull out heat, which of course for power amplifiers, you're generating tons of heat as the device operates. And so here's how Soctera is incorporating this material. So if you took our wafer and cracked it in half and you looked at it from the side, this is what you would see. In contrast to the conventional GaN structure shown on the left, we've incorporated aluminum nitride with its superior temperature control as the heat sink for our devices. We've incorporated a very thin gallium nitride channel, just 15 nanometers, to take advantage of GaN's unmatched speed performance to still maintain that high frequency range. And finally, we've incorporated an aluminum nitride barrier, which is what dictates the maximum power at which your device can operate. And so as a result of the incorporation of aluminum nitride, we expect it to provide up to 2 times the power that GaN can currently provide in the millimeter wave frequency band. And this translates to 40% more range for telecommunications and defense radar. And the reason that we are the company to lead the aluminum nitride revolution is our expertise in developing world-class aluminum nitride material. And it's made in our labs, 1 atomic layer at a time. Our lab has spent over 10 years developing this material with over 2 million grants towards the technology. More recently, we filed 3 patents based on aluminum nitride electronics. So our team is comprised of myself, my fellow PhD colleague Reet, and our 2 advisors, Professor Grace Jing and Devdeep Jena, both in electrical and computer engineering and material science. And together we founded Soctera. And thus far in Soctera, we participated in the NSF I-Core program. This was last year before the shutdown, so we were able to travel to many defense contractors and telecommunications companies. So some examples, Raytheon and Lockheed Martin for defense, and Nokia and Ericsson for telecommunications, and indeed found the problem was ubiquitous among the program managers and the engineers that higher power is what they're constantly looking for their power amplifiers. And perhaps most exciting is the fact that together with Reet, we've been able generation of aluminum nitride power amplifiers in the world. So as of today, we are working to build on our academic success and develop a commercially viable amplifier. So of course, there's differences in designs and the complexity from a simple academic amplifier and the commercial product. But this is what we're working towards right now is our minimum viable product. And then after this, technology to bring the and I should also mention that we are currently applying D, and which ideally we will accept once Reet and I graduate this coming spring. So to summarize, millimeter wave range is the critical pain point of defense radar and telecommunication systems. We know that the range is improved with power, and more power is provided by better materials. And to truly unlock the millimeter wave frequency power performance, the material of choice is being developed by Soctera. And with that, I will stop and take any questions that you may have.
Excellent. Thank you, Austin.
Yep.
Okay, who's going first?
I'll do a relatively easy one. Do you know of anyone else who's innovating in this space? Do you have any competitors?
Yeah, so we do know, so yeah, there's a lot of, just to kind of answer 2 questions, another question in addition to yours, aluminum nitride has been around for a while. and it's actually in our cell phones already, but as a filter. So this material is sputtered, which is a lower quality material. So that's really where we're able to differentiate ourselves from a lot of competitors, is the quality of our material enables us to even make power amplifiers in the first place. So we do know of about two companies that are working on this, but they're more focused, they're more materials focused companies that don't actually make devices themselves. They don't have a fab. They're really just focused on material growth. So that's kind of the unique part that we bring to the table, is that, and really unique, not just in companies, but in terms of academic labs, is that material research and device fabrication are further apart from each other than you would think. And our lab is able to do both, actually all of it in Duffield Hall. So we're able to go from literally putting the aluminum and nitrogen atoms together to measuring the final amplifier all in the same building. And so that's kind of our really unique capability that sets us apart from the couple of material companies that are also looking at this. And it's the reason why we were the first to demonstrate aluminum nitride based amplifiers.
Super.
Austin, you had mentioned that the market was 2 billion. Is that what you think the total addressable market is here? It seems like that seems small compared to how much.
So that market was specifically for RF gallium nitride power amplifiers. So just that component, not the overall telecommunications or defense, but yeah. So the markets that GaN RF amplifiers are currently fulfilling, and so that's kind of that's the only competitor at that frequency that we have. So that's I guess my way of defining the market that we expect to be entering. And yeah, like I said, I mean, it is small right now, but GaN really just came on the scene in a big way within the past 5 years. So it itself is really new as well. So it's rapidly growing as well. Yeah.
So just a quick follow-up on that. So GaN, the spend on GaN amplifiers right now this year is 2.5 billion. And how many companies supply those?
Yeah, so there's a handful within the US. I'd say probably around 5 or 6 like would be the over 90% of the market. And yeah, so they are, they aren't startups, they are large, semiconductor manufacturing companies. So that of course will be one of our main challenges, is being able to scale up. And so the way we would have to do that is using a fabless semiconductor company model, which is actually the most common by startups today, which is of course where you don't do the fabrication yourself at a certain point. Once you've done the proper demonstrations, you contract the foundry to do that for you. And that allows you to scale up. But yeah, so to answer your question, there's about 5 or 6 large scale companies currently supplying gallium nitride amplifiers.
Thanks.
Yeah.
Go ahead, Steve.
I can throw in a quick one. If Soctera is wildly successful 5 years from now, what's the elevator pitch for how people describe it?
So yeah, the elevator pitch, it's I mean, it's centered on aluminum nitride. It's aluminum nitride has enabled I want to say defense radar and telecommunications, but honestly, like when you move into these frequencies, there's all sorts of new medical applications and unforeseen applications. As you like, just to give you an example of what GaN has been able to do. Sorry for a tangent, but they were able to create this network of GaN amplifiers that is currently scanning the skies and can track all space debris orbiting Earth to make sure it's not on a collision course with the International Space Station. And so that's like, in a way to answer your question, like that would have never even, that wasn't even thought to be possible before GaN. And so you know, if you're able to truly unlock that power and millimeter wave range, I can tell you the applications that we know today, but in truth, there's going to be probably a lot cooler ones that I'm not thinking of right now. Yeah.
So I think the answer, Steve, I think the answer is Soctera, vision for the world,
Yeah.
or vision of the
That's
world.
good.
Yeah.
Something like that. Something
Yeah.
like that. Okay, Austin, thanks so much for your time.